One of the research topics on the vocation project is the scalable reconstruction and exploration of complex indoor environments. In this context, one of the targets has been the creation of novel methods for automatic structure 3D reconstruction from sparse and noisy data of indoor environments. In this pilot, we showed the applicability of the developed techniques to real data in the architecture, engineering, and construction domain, and demonstrate integration with the prototype mobile mapping system developed within the project. The primary focus for this research direction is on panoramic 360-degree images, such as those captured by a variety of commodity and professional devices, including the prototype mobile device developed within the project. Here we saw how, by using the advanced methods developed within the project, it's possible to exploit the panoramic images to rapidly upsample and complete sparsely acquired depth, for instance, from a single rotation of the mobile laser. We also saw how it's possible to exploit priors on the acquired environments to extract structure information, 3D layouts, even without any supporting 3D input. Going beyond geometric reconstruction, we also saw how it's possible to visually and geometrically remove clutter from acquisitions. All the techniques share the common idea to exploit data-driven prior knowledge and deep learning methods to discover hidden relations from large data collection and exploit them at inference time to cope with partial and noisy input. Let's start with the first contribution, the recovery of a full dense depth map from purely visual input, in our case, a single panoramic shot. Our dense depth estimation technique was first described in our CVPR 2021 contribution. In that work, we introduced a novel deep neural network solution, dubbed SliceNet, which predicts the depth map of an indoor 360-degree image. The method is capable to infer depth without any supporting 3D input and can thus complement the usage of the device that combines laser plus depth. Fast depth estimation from single images is a fundamental subproblem of indoor reconstruction, since associating metric information to visual data is paramount for a variety of applications, including mobile augmentation reality platforms, indoor mapping, autonomous navigation, 3D reconstruction, and scene understanding. We start from the assumption that capture of the scene through an equirectangular image is aligned to the gravity vector, that is to say, camera is placed on an horizontal ground plane, and thus it's rational to assume that gravity-aligned processing of images can directly exploit gravity-aligned world space features. In our network, an input equirectangular image is partitioned into vertical slices by performing a contracted encoding to reduce the input tensor only along the vertical direction, resulting in a compact and flattened sequence of slices made of a set of features. To preserve global information, we perform slicing over 4 different resolution levels, concatenating the result at the end. This sequential representation enables the use of a convolutional long short-term memory LSTM network to recover, with low computational overhead, long and short-term spatial relationships among slices. The coding proceeds symmetrically with respect to encoding, thereby increasing only the vertical resolution of the feature map until the target resolution is reached. In the original article, we report on tests of our network on both synthetic and real datasets, obtaining on 4 common publicly available datasets to facilitate comparison. These benchmarks were also adopted by the recent state-of-the-art work comparable with our method. The results demonstrated that our method outperforms current state-of-the-art methods in prediction accuracy, especially when working on real-world scenes. See the original article for more information. For this pilot, we tested our network on unseen and real data by the mobile mapping prototype developed within the project. We randomly selected a number of RGBD panoramic captures, creating a test dataset consisting in 149 RGB panoramic images, coupled with depth information that provides ground truth. The capture was made inside a building and composed of one room, 2 corridors, and 1 stair landing. To evaluate our model on this dataset, we used the panoramic images acquired by the device's Garmin spherical camera as input, and we used the depth maps provided by an acquisition of the same environment using a Faro Focus 3D X330 TLS as ground truth. This setup makes it possible to show a quantitative and a qualitative evaluation. For testing in the most challenging situations, we didn't retrain our model on such novel scenes, but we used them as an example of transfer learning capability. Results show our method still achieves good results without the need for a specific retraining, although the original training set was acquired with a completely different setup, that is a Matterport static station calibrated to ground, without upper and bottom hemispheres, while here images have been captured with a mobile setup with varying alignment to the ground. In particular, despite the fact that captures were processed without enforcing the gravity alignment prior used in our method, the results obtained are visible acceptable. Moreover, on a NVIDIA RTX 2080 Ti, single GPU inference time is 74 milliseconds for a 1024 x 512 image, showing that our method can be integrated in interactive settings to perform frame-by-frame depth inference from purely visual data. In our second contribution demonstrated here, we introduce another technique dubbed Deep 3D Layout that exploits a graph convolution network to directly infer a watertight 3D mesh representation of the room shape from a gravity-aligned panoramic image. The work has been presented at SIGGRAPH Asia 2021 and published in AEC Transaction on Graphics. As for the first dimensional indoor spaces, deep learning solutions have emerged as a very promising way to cope with these problems. However, 3D layout reconstruction is more complex than depth estimation, since it doesn't simply assign a depth to each visible pixel, but must extrapolate large portions of the invisible structure, which can be occluded not only by objects, but by the structure itself, leading to multiple intersections per view ray. Our end-to-end deep learning technique maps an rectangular image to a 3D mesh representing the bounding surface or the room. Two graph convolution network blocks the form an input icosphere by offsetting its vertices. The first block starts from at first pulling of the gravity-aligned features to return a low-res estimation of the mesh. This low-res representation is then refined to pull refined gravity-aligned features which drive the second graph convolution network block. The output of the second block is the final refined mesh model. Our knowledge of the indoor characteristics drives the design of the network. In particular, gravity-aligned features take into account the existence of preferential direction. Moreover, they are actively incorporated in the graph in a projection layer that exploits the recent concept of multi-head self-attention to cope with occlusions, exploit large-scale regularities. In the original article, we tested our network on publicly available benchmarks. For illustration, we show here respectively the input rectangular image, the ground truth 3D model, our predicted results, our prediction with the ground truth overlay, and the prediction with a competitor method with ground truth overlay. The results show that our approach guarantees consistent performance with different kinds of models, in particular in the case of more complex structures such as domes and sloping roofs. See the original article for more information. Since the vast majority of the commonly used public datasets and benchmarks consist of Manhattan world scenes, in the Vocation project we created, tested, and released a new synthetic dataset named Pano 3D Layout that covers many of the cases not found in the standard benchmarks. These include more challenging cases such as domes, slope, or step ceilings, and more. This dataset provides the ground truth data as watertight meshes so that they are compatible with common 3D mesh reconstruction pipelines and needs equirectangular images. We tested our methods even on this novel dataset, comparing the results with competing methods which have best performance on the same data and for which training code has been made available by the authors. The results show that our approach guarantees consistent performance with different kinds of models, in particular in the case of more complex structures such as domes and sloping roofs. In this pilot, we also tested the method without any retraining on panoramic data coming from the prototype mobile mapping devices. Specifically, we performed a test on unseen data which mostly violate gravity alignment assumption. Since the original baseline is trained on fully gravity-aligned images and meshes, misalignments of mobile captures should inevitably result in mesh deformation. We can predict the results starting from a 512 times 1024 image at a rate of 27 frames per second on a single NVIDIA RTX 2080 GPU. The figure shows how just using a single shot RGB capture, the method is able to estimate a plausible 3D layout. In our third contribution demonstrated here, we have also studied methods for generating variable visual and geometric models, especially in the context of extended reality applications. Here we show results on room M-Time. This work has been presented at ISMAR 2022 and was published in IEEE Transaction on Visualization and Computer Graphics. The tackled problem consists in transforming a single panoramic image into a representation of visual and geometric representation of the uncluttered room, where we define clutter as all the objects that are not part of the room's architectural structure defined by walls, ceiling, and floors. The model architecture consists at first processing the input panoramic image to identify the cluttered area in the scene, exploiting a separately trained lightweight network. Then the returned clutter mask and the original input image are then passed to the empty scene synthetic network, which returns the photorealistic equirectangular representation of the M-Time scene and its registered depth. The first stage of our method consists of an identification of the area containing the clutter that should be removed from the image to generate the empty room color and depth panoramas. This identification consists of a binary mask that contains 1 4-pixel containing clutter and 0 otherwise. To generate the empty scene image and depth, we adopt an overall encoder-decoder scheme follows a common design for image in painting, exploiting dilated convolutions as bottleneck and gated convolutions for encoding-decoding. The input of the network is thus a single-shot 360-degree panorama of cluttered room, which is transformed with low latency into a panoramic image depicting the empty room, together with a registered depth map. Here we saw an exploration around a panorama of a cluttered room as input and the output of not just its empty room but also its registered depth map. By inferring the room's geometry while removing clutter, We provide support various scene edits, including adding positioning furniture while resting on floor or attached to a wall. The method was trained on synthetic data and tested in a variety of settings. The originally presenting results show that our method is able to predict completely empty scenes on real data, automatically removing various types of clutter and very heterogeneous furniture. See the original article for more information. In this example, we saw its application to panoramic data captured by the project prototype mapping system without any retraining. These results thus present qualitative performance on data for which no ground truth and training set was available. This situation is the expected usage of our method. To illustrate very difficult cases, we have selected examples when capture is not aligned to the ground and when the user is visible in the cluttered scene. In our fourth and final contribution demonstrated within this pilot, we move from purely visual input processing to data fusion. We report, in particular, on results obtained with our novel end-to-end deep learning solution for rapidly estimating a dense spherical depth map of an indoor environment from both dense visual data and sparse geometric data as input. Since our work is under review, we only provide here a brief illustration and show examples of application to project data. A large variety of setups include both high-resolution visual input and panoramic depth information. In this image, we show two examples, the prototype device improved within the project and the common Matterport 3D camera. Since the visual channel has denser and higher resolution information and can typically be acquired very quickly, there is an interest in using it to improve the quality of depth information. However, the sparse output from various kinds of sensors imposes fundamental challenges on machine learning methods, since data relevance is not uniform and further processing is required to either reconstruct or ignore missing regions. Here we can see different kinds of sparse depth, such as the sparse depth map by a Heron LiDAR has lots of valid information, but only for a few stripes. And by a structured light sensor, a Matterport Pro 3D camera, which has lots of missing areas when rooms are large, surfaces are shiny or thin, and strong lighting is abundant. Our technique solves this problem through a specialized method that builds on our previous work on depth estimation for pure visual input. Since the work is still under review, we don't provide details here, but only illustrate some of the results obtained on project data. For the pilot, the mobile mapping device used and improved within the project can be seen as a LiDAR RGBD acquisition, that is to say, mobile device with a registered Garmin spherical camera that provides a panoramic image, and two Velodyne VLP16 that obtains a sparse depth map. At each laser rotation, the device is produced just a sparse depth information, which can be projected in the inference frame of the panoramic camera to produce an omnidirectional RGBD input with a sparse depth. The same scene was acquired with a Faro Focus 3D X330. Projecting the dense point clouds to the panoramic images, we can have a dense RGBD representation that can be used as ground truth. We show here the application of our method to the project data, illustrating the estimation of a full dense depth map starting from a panoramic image and data coming from a single LiDAR rotation. This figure shows examples of scenes acquired with the mobile backpackage device and how our methods successfully complete the map on data for which no ground truth and training set was available. Here, a complete sequence of the input at the top and our results at the bottom, demonstrating the low latency, high frequency applicability of our solution. In our case, starting from a 512 times 1024 image and depth map, we inferred depth in under 16 milliseconds on a single GPU, which is much faster than a single rotation of typical LiDARs covering a 360-degree view. For instance, 50 milliseconds to 200 milliseconds per rotation for a Velodyne VLP16. We can in particular generate 2K times 4K depth images from equally sized inputs in less than 0.4 seconds. As a conclusion, the pilot has shown that the Vocation project has achieved significant results in the creation of novel methods for the automatic reconstruction of 3D environment, with a particular focus on panoramic image and on their fusion with sparse depth data.